Hello and welcome to The Chemist from The Economist. I'm your host, Ben Al-Haddad. Co-hosting with me is Sophia Melamed and with sound engineer Gabriel De Romana. Every weekday we provide a fresh perspective on the chemistry shaping your world. Question 1 most certainly didn't act like your usual chemistry exam question. It shifted exam statistics farther and worse than any other before it. We ask what it is and what it means for subsequent chemistry. Dr. Tavar is a professor of chemistry at Johns Hopkins University. He earned his PhD at MIT and leads a research group focusing on the synthesis of organic carbon-based molecules with Pi-Conjugated systems. Dr. Tavar, what are molecular orbitals in Pi-Conjugated systems, and how do they relate?
So molecular orbitals describe electron partitioning within molecules. And in the context of pi conjugation, you're looking at p orbitals that have not been hybridized when you think about making sp3, sp2 hybrid orbitals. The p orbitals remain unhybridized, and these are higher energy levels and they're more accessible for electronic transitions. And so molecular orbitals describe certain subsets of energy levels, or they describe how electrons are partitioned within an energy level. And in the pi-conjugated systems, these energy levels that we're dealing with are accessible within the visible energy range. So you're able to have transitions that visible light will allow for absorbance into higher excited states.
And as you said with the sp1, sp2, sp3 orbitals, do the atomic orbitals have a part in constructing them?
Yes, so actually the p orbital is an atomic orbital. Mm-hmm. So when you have a chain of conjugated carbon atoms, the other s and p orbitals have been hybridized to make sp2 hybrid bonds, sigma bonds within the network. And the p orbital is the dangling unhybridized atomic orbital, the pz orbital, if you want to call it that it's maintained along the chain.
And the molecular orbitals that are constructed by the non-involved AOs, how do we know that those don't have a part in constructing those perpendicular to the, plane of the molecule?
Yeah, so basically thinking about constructing molecular orbitals, it's mix and match of math, right? So you are selectively taking 2p and 1s and you're mathematically mixing them together to make the sp2. You can selectively mix 1s and 1p to create an sp hybrid, and then you have 2p orbitals that are free. It basically is something that's been parameterized to fit an experimental observation. So we know the geometry of methane, sp3. We know the geometry of benzene, sp2. And so the math is helping to get us to the answer that matches the physical observation.
Mm-hmm. And in terms of the math behind that, our textbook says that MOs are the results of linear combinations. What exactly does that mean?
So these are where this is the mixing and matching, where you can take fractions or whole elements of these atomic orbitals and mix them together to be able to create new geometries and new structures. So this, for example, with methane, we know experimentally that methane has a tetrahedral geometry. So we can mix the s and the 3p orbitals together to be able to have the 4 points of the tetrahedron. Other geometries that we know are planar, like the pi-conjugated systems, we know are sp2 hybrid, so we can fix the math to allow us to have 120-degree angles between the sp2 hybrids. At the same time, you can start to reconstruct, and it becomes a little bit more difficult where you have different hybridizations on the same atom. Some bonds can be more p character, other bonds can be less p character. It's all about the math to fit into the experimental observation. On the flip side, if you look at methane, which I've just said is tetrahedral, if you look at some of the electron spectroscopy of methane, photoelectron spectroscopy, you'll see energy levels consistent with 1s and 3p orbitals, so indicating that it's not hybridized. So it really is something that it's a mix of both, where you can think about structure in terms of just s and p orbitals, or you can think about structure in full sp3 hybridization.
And for the math involved with combining these atomic orbitals, we see with pi-conjugated systems that you can have multiple molecular orbitals, and with alternating, positive and negative regions. How is it that we can have, for instance, one p orbital be positive, on the upside of the plane for one MO, but negative on the next?
Right, so this is just a function of the mathematics. The signs don't mean anything physically. This is just indicating the phasing of that orbital. So it isn't indicating positive or negative in sign or indicating some Coulombic attraction or repulsion. This is just the mathematics of the function. And so as you know, when you're thinking about actually calculating the overall electron distribution, you would square those numbers, right? And then that would lead to the phases would be canceled out, or the numbers, the signs would be canceled out. But the phases are just in terms of mathematical bookkeeping. And so based on how you construct those orbitals, you can have inversions in one level and they maintain the same in another level. It's just a matter of how the math combines.
I would like to sort of talk to you more on the application side of this concept. You have been doing research on materials with extended Pi-Conjugation, which have interesting properties such as luminescence and light harvesting. And in our exam in particular, we had to deal with beta-carotene, which is light harvesting organic compound. And that was an example. So maybe you could explain how Pi-conjugated systems interact with light the way they do to produce these properties.
Okay, so when you set up any kind of molecular orbital, so starting from groups of atomic orbitals, you'll create a series of energy levels. And those energy levels are, again, the gap between those energy levels can be calculated depending on the structure. And that gap dictates any kind of transition between energy levels. And so it turns out, coincidentally for us, just like metal complexes have brilliant colors, those are associated with D to D orbital transitions. It turns out that those energetics are within the visible wavelength of the electromagnetic spectrum, meaning that if energy is able to impinge upon a molecule, that energy that is impinging will be sufficient to excite into a higher energy state and absorb that photon. Same with Pi-conjugation. It turns out that the nature and the energetics of the overlap of the p orbitals that make up those Pi-conjugated systems are just in that energy window to be able to absorb UV visible region of light. And so therefore, as you start to tune the length of the Pi system, you change the length of those energy state, the gap, that energy gap. And therefore, you can have different colors based on the size of your Pi-conjugated system. So beta-carotene has, 14 double bonds, I believe, or something, or 14.
Something around
I think
that.
it's
7.
11.
Is it 7? Well, it has a lot of p orbitals, a lot of p orbitals in a structure. Right? And so those, as you add more conjugation, what happens is you raise the energy of the HOMO and you lower the energy of the LUMO, and it keeps, as you add more, it keeps shrinking and shrinking and shrinking. So when you get to things like beta-carotene, you have a very small energy gap, meaning that it's able to absorb very low energy or very long wavelength light, which is why it's appearing in these deep reds and oranges.
So it's all about having a small gap between the HOMO and the LUMO as possible.
Exactly.
It's very interesting. All right. And our final question is, could you please tell us about the applications of the Pi-conjugated systems in your most recent research?
Okay, so within my group, we study a lot of pi electron systems and their energy transport processes. So as it turns out, just like we're able to have energy gaps defined by the length of the molecule, these molecules, as they start to self-associate, can create other types of pathways for charge or energy delocalization. And this is something that we try and capitalize on by being able to design new molecules that have specific energy requirements or specific energy outcomes in terms of their transport properties. And also their plastics, their dyes. And so all of the technology that you think about to process a dye, humanity has painted things, right? Inkjet printing, tattooing, all of these types of technologies with the paintbrush, can be used to make a material that can absorb or emit light. And that absorption or emission can lead to things like energy harvesting or storage. You can have light emitting, for energy, for display technology. And then we're also moving in the context of thinking about biomaterials that have pi electron segments within them that we can take advantage of for biological energy transport, being able to think about mimicking biological processes such as photosynthesis or signal transmission through nerves, things like this that are inherently electronic. We can now couple into these artificially.
All right. Thank you very much.
You're very welcome.